I'm trying to imitate Bernie at the election. It goes like that. Take it easy. But as you can see from this picture, I'll be talking about some pretty weird stuff. And it took me a long time to decide to sort of take this step into the unknown and talk about stuff that I never talked about before. So this is a very sort of prototype talk, and it's going to involve a lot of science. As you can see here, there's a brain, and there's Einstein, and computer, and whatever. I want to say, and because I keep being introduced, not you, but I keep being introduced as an Egyptologist, and I'm not an Egyptologist. Frankly, I'm not a scientist. I'm not an archaeologist. I'm not any ist in that list. Okay? No ists. I'm a bit of an ear thing. I'm an engineer and maybe a pioneer, okay? However, there are people who have given me ists, like the man with the hat, you remember him? Dr. Hawass. You know, he's given me a few ists, like pseudoscientists, pyramidologists. So, you know, I've heard all the labeling. But what spurred me, first, we have a little disagreement, right? So the talk is about what is the true purpose of the pyramid, right? And it's been checked at the highest level. Right? Sorry. There's this very cool site. I don't know if you've seen it. You can put whatever you want to put on there. Right? Okay, there we are. Okay, here is what it's all about. And in the picture you can see, well, me. Next to me is Professor Chandra Wickramasinghe. Chandra Wickramasinghe is an astrobiologist, and he has been teaching astrophysics and astrobiology since the 60s. At Cambridge, he was a student and a collaborator with Sir Fred Hoyle, and together they proposed the famous Panspermia theory. You know a bit about Panspermia? Okay, we'll talk a bit about that. And the other guy looking sort of with his head down is Dominik Görlitz. Dominik Görlitz is, I don't know if you heard about this cartouche scandal that these Germans took the samples from inside the pyramid. And of course, the guy in blue is the naughty guy. Is Eric von Daniken. And I've been friends with Eric von Daniken for 20 years or so. And he knows that I do not approve of the way that certain evidence has been presented. He knows this. We're good buddies. But I was, and now even more so, very open-minded to the core idea. And the reason I would like to present it. So we have, here is, I think, this is a new thing, there we are. They pioneered the astrobiology. Actually, the term astrobiology was coined by Chandra Wickramasinghe and Sir Fred Hoyle in the late 60s. And they proposed, of course, the Panspermia theory while they were at Cambridge. And the reason I got with him is that he underwent the same grilling as I did. You know, as maybe Andy knows as well, when you present a new idea and a theory, you stir up the opposition, and in their case, it was pretty violent, to the point where even their scientific papers were not published. There was a kind of moratorium and a blacklisting. So of course, when I published The Orion Mystery and I got the same treatment, he contacted me and we became friends. And this was about, 1994, 95. We lost touch. We went to a few conferences together, but finally we met, and where you saw the picture before with Eric von Daniken, we met at a conference, actually at Eric von Daniken's 80th birthday in Stuttgart. You were there. And the idea came to try and write a book together, me and Chandra Wickramasinghe. And I said, well, what about? And he's now retired, and he feels that he ought to say what he has in mind. And we're talking about Mr. 6 PhD here, two from Cambridge, awarded, won several physics awards. I mean, he knows his stuff. And I was very surprised because, I mean, the stuff that I was extremely reticent to talk about, like maybe extraterrestrial contact or other strange ideas about the possibility of these ancient monuments, especially the Great Pyramid, he was refreshingly open, I mean, amazingly open, and we got chatting. And he said, look, I mean, the problem is that we're obliged to consider many things because of what we know today. And this is what I want to do. So it's not that I want to sort of do a teaching lecture here, but I said, well, I mean, I've been out of this. I mean, and he said, well, look, you're still in the classical world. You're still living in what today physicists call the classical physics. Newtonian physics, Einsteinian physics, the general law of relativity. And this works very, very nicely. I mean, we send people on the moon and all this for the big stuff. You know, for you, me, rockets, stones, apples that fall from a tree and all that. But the thing is, you know, since the 1920s, and certainly the evolution of the new physics, which of course is quantum mechanics, we're obliged to consider all sorts of things. And we don't like it. We don't like it because the understanding of what it's opened up, I mean, the reason you have cell phones and iPads and the reason I'm showing you slides digitally is because of quantum mechanics. It's provided us with a completely new technology. But it's unfortunately created a situation where it's counterintuitive. Counterintuitive is that we know it works. They can calculate it to the extreme precision. They can send a message from the other side of the world. You get it on your phone here. You even get an image. But we don't know why it works. It's one of those things, and nobody has been able to explain because it's so counterintuitive. I'll get into it later. It's really, you have to go against your common sense. You have to go against your logic. And it forces us to consider what we don't like to consider. It brings us again back to considering things like a created universe, extraterrestrial contact. It forces us to consider the soul, consciousness. We have to get into this because it's taking us there. And that's the exciting thing today about science. And I know there's a lot of antipathy for science. You know, we say science and the spiritual, but they're finally meeting now. And that's where I get interested. That's where I get interested because not only it's extremely exciting that you're on the edge of a situation where these very stubborn physicists, very ground earth, you know, Newtonian thinkers, Einstein thinkers, people who send people on the moon, you know, and they work with machines and all this, are forced to consider what they felt very uncomfortable to consider. They're forced to. And that's where I come in. Because I said, okay, well, let me update myself, and this is what I want to do here. Now, some of you may be updated, I don't know. We'll have fun doing this. Now, unfortunately, to update all this, you need to know some mathematics. And I hate mathematics. I flunked it at A level, there you are. And so I won't do the mathematics, and I don't suggest you do. It's very exotic mathematics. So, but we don't need this. We don't need this. We need to understand what it's about. We need to know where we stand on the edge of science. When you get there, then you can look at things from this point of view, rather than from the classical point of view. And what I mean by the classical point of view is when you talk to archaeologists, as I did 25 years ago with my theory, they went bananas because I just said 3 stars look like 3 pyramids. But now, I've got a picture of Galileo here. There you go. What does it say? You know, I love this stuff. Thank you, Condis. Mathematics is the alphabet in which God has written. Oh, never mind. How come we don't?
Because he doesn't have a phone.
Oh, don't worry about this. I know what it says. It says the universe, right? I was tempted to say me, but mathematics, yeah. It's true. It's true. And people say, well, woof, we don't like a mathematical universe. I mean, it sounds like, no, we want it to be spiritual, and it's about consciousness. And what's this about mathematics? Well, mathematics is just a tool. It's a language, actually. It's just a language that if you are to understand the universe, and even consciousness, and even the soul, you need to understand it through its language. The universe talks in this language. And I was having a discussion all day with a friend of mine, and this afternoon with André de Smet, who is an old friend of mine. And I gave one example, a very simple example. Mathematics allows us to stop the argument and to force us to consider what comes out of the argument. 2 and 2 is 4, that's it. 4 and 4 is 8. No argument. But what does it mean? And then it forces you to look into this. And this is why we have to marry again. We have to stop thinking, science is for the scientists, the people in white, and we are the spiritual people, and we think very differently. Yes, but they're joining up, and this is what I want to tell you. They are now coming on the same edge. And the spiritual people will have to start thinking a bit more about science, and the scientists will have to start thinking about this. We're meeting up, because that's where it is today. So let's do it. Let's do it. Oh yeah, dear math, please. Oh, yeah, there we are. We all hate, who loves maths? I stopped at calculus, by the way. I went up to O level, it was fun. But then when we got into A levels, and I'm talking about like 40 years ago, I don't know what they do these days, but the minute they start talking about calculus, that's it. My mind stopped, and I just said, please, I want to pull out. So I'm not going to do mathematics, all right, don't worry. But nonetheless, bear in mind. So I'm going to be talking about where we stand today in cosmology. And I want to tell you what not only it's an update, okay? I call this an update. It's like you update your computer. I'm going to update myself, my mind, and I hope I can get you there so that we can start looking at things like theories and the possibility of pyramids being located, something to do with Orion, something to do with Cygnus, more intelligently, more from an update, rather than being called you're nuts and all this stuff, all this nonsense that goes around. So this is backed by where we stand today, even though it may be weird. And let me tell you, there's nothing more weird in this world than quantum mechanics. I don't know if some of you have gotten to it. It's the weirdest of things. I mean, it's completely crazy. Something can go at the same place at the same time. There's multiple universes and infinite universes, and you could be sitting here and could be sitting somewhere else. It's just totally weird, but it's true. And this is one of those things. It's a bit like Galileo. Since I had Galileo, it's getting out of the Inquisition and saying, I'm sorry, but the damn thing turns. And nobody wanted to believe it. I generally give this little metaphor. I'm going to walk around. I'm one of these. I'm half Italian. I can't stick it out. Never mind. There's a mic. Okay. 500 years ago. In fact, I'll do a bit of publicity. I wrote a book about the Vatican 2 years ago, called The Vatican Heresy. And it's all about the trial of Galileo and Giordano Bruno and all this stuff. And 500 years ago, you would go in the streets, even in London, but certainly not in Rome, because if you'd say to people, the Earth is a globe and it goes around the sun, and there are other planets going around the sun, and it turns in 24 hours, and you don't finish saying this, they cart you to the Inquisition, and you get burned at the stake. You couldn't say this. And people laughed. I mean, if you said it to your friends, they would laugh. Now you go in the street and you tell them the same thing, and it's totally kosher. No problem at all, right? Anybody has problems with this flat earth people? No? Right. But if you go in the street and you pick anybody, well, you might be lucky. Not the distance. You might be lucky and you hit the right person, but the odds are against you, and you say to somebody, look, you're here, but you could be somewhere else. And I think there's an infinite number of universes, and my arm that has atoms could be in the arm of Donald Trump. And when I move my arm left, his atoms move right. And they look at you, and they might call the ambulance and have you picked up with a straitjacket. They would, or some people would. If you tell this to a theoretical physicist today, it's totally okay. In fact, Nobel Prize winners, we've had Professor Weizmann, who got a Nobel Prize, who actually made a comment lately, and various others, Michio Kaku. Anybody follow Michio Kaku? It's like, okay, it's totally normal. In fact, some of their theories are even weirder than this. Why? It's not just because they come up with crazy theories. It's that the language tells them that this is a possibility. They can't prove it yet, but the language says so. Now what all this, okay, let me move on. So, cosmology, right? Quantum mechanics, I'll leave it. The brain, my favorite subject these days. And we're going to talk about the brain. And my daughter said, this is awful. I mean, show a picture like this. Well, that's what's in your head, by the way, this lump of 1 kilo, 300 grams, mushy. It's the most fantastic thing. Michio Kaku, who I met once, told me there's two things that are the most fantastic thing, the universe and the human brain. When you get into there, you realize, my God, I've got one of these things. I was going to do a little experiment, but I'm not quite sure. I was going to ask somebody, probably my daughter, and say, in fact, I'll do it. Why don't I do it? Here's the hat. I wish I had 2 hours. I was going to, okay, this mat. I'm going to throw this at you, and you're going to catch it. Good. So what have we done? Oh, damn it. Yeah, let me try this. Help? Can you hear me? Yes. Ah, good. Ah, that's better. Yeah, I'm free. It's okay? It was just picking this mic. Okay, well, the simple answer is Robert threw the hat, and André de Smet caught the hat, right? Right? That's what happened, no? Well, I'm estimating here, but I've had it checked, we discussed it with. There's been something like anything between 1 trillion to 300 trillion calculations that his brain has done just for this act and looking at me. And that's what happened in there. And I don't know what these calculations are. Because all the laws of physics, all the laws of nature have been applied in the flick of a second here. Tossed it. I knew somehow at what force I have to give it. I weighed the hat. He judged the distance. In an instant. There is, if a computer was going to simulate this today, and we don't have it yet. I know people say, yeah, we have a computer. No, trust me, we don't have a computer who can do this. But to have a computer do this, we'll have to increase its power by 2,000, which we don't have yet. Your laptop, which is quite extraordinary, this phone. It will have to be the size of Mayfair, probably. It will have to have a power plant to run it. And you have that lump of flesh, and you run it, well, with 2 hamburgers, if you like hamburgers, or 3 spoons of sugar. And it does this. We all have it. All the knowledge of nature, all the laws of nature were done by both of us, and we have no idea how it's done. We know we decided to do it, but we have no idea. If I was going to have André Smet as an artificial robot, and I'm supposed to give him a brain, an artificial brain, I don't have it. It will have to be the size of Mayfair. But we may have it in 20 years' time, they think, 30 years' time. But it still won't be able to do this, because we'll have to program it as well, not just to have it its capacity. It's an extraordinary thing. And I'm new to this, and I walk around now and saying, my God, every time I move my hand, I'm doing 3,000 million calculations and all that. But it's true. What does it mean? Can we access this? Can you sort of link up and know, well, it's done? Well, hopefully not. because 3 trillion calculations in one go in 1 second, you don't want this. You'll blow your mind, literally, your conscious mind. But maybe you can access part of it. And this is where it gets interesting. And I'm sure you've followed, at least perhaps some of you, Daniel Tammet, right? You know, the super savant genius, been on TV many times here. They don't know how they do it. There's another one called Wolfgang Pauli in the 1940s who got Nobel Prize winner, one of the founders of quantum mechanics. He was convinced that it came in his brain, all these formulas, and the reason he could explain them, I cannot, the Smet cannot, and I tell you why we cannot, because we don't know the mathematics. If he was a nuclear physicist, a cutting-edge physicist, it'd take him hours, but he would be able to work out all the actions that we took. It would take him days. A computer would take about a week to try and work out this very simple action. These people were convinced that they could get it here. They just got it. We get it all the time. Now, not the laws of physics. You have a thought, right? You think, I like this poster. I like this food. How do you tell the other person that you like this? You're translating a thought, and you're using the alphabet of English language. You mix up your thought, and it comes up in words, and the other person understands what your thought was. Well, the same thing with mathematics. That's what Einstein did. He had a thought, and he thought, wait a minute, or Newton, perhaps more easy, he sees the apple fall, he says, what's pulling it down on the ground? Many people have probably wondered, why is the apple falling? They didn't have the language. Actually, Newton had to invent calculus in order to explain it to others. He spoke the language of the universe. And that is what we all can do. Either you're going to learn the mathematics of it, which will take 15 years, by the way, so unless you're that keen. And it's very few people can do it. But we can at least know that this exists. And that's where science comes very interestingly, because it's beginning to touch the ethereal. It isn't just mechanical action. He's been thinking, well, why is Robert doing this? You know, why is he asked me to catch the hat? He's looking at me and he's, well, I'm looking at you guys, I can't see too much. But just at one glance, I'm catching about 40,000 images. That's the average, they say. And in fact, I'm not catching images at all. I'm catching the light that's coming to me through photosensitive cells in my eyes. There is literally millions and billions of them, and they transmit a message in the brain that converts them into images. I can see your face, I don't know why I'm looking at you all the time. Your face, and I know who you are. There is no computer in the world that can recognize this. They have computer identity checks, but you have to tell the computer and show in the image all this business, and even then, because the minute you turn the image, it doesn't recognize it anymore. You see a car, and you know that this is a Ford, this is a tree, this is a church. You recognize things instantaneously. This is what happened. So it isn't just catching the hat. He's been doing all sorts of crazy computations there to tell him what is this and what is this color and why am I looking at it. It's an amazing processor. And we all have one, and we all are as good, true, as Newton, as Einstein, as all the geniuses. The only difference, we don't know the language. So, but what if, and this becomes very interesting, because we have the what ifs. We have the super savant geniuses that brings us to this what if. They tell you, I don't know how I do it. I don't know if you follow this Daniel Tammet. He can tell you pi, which is an infinite number. He can recite pi to 22,000 digits. I know it up to 4, and that's as far as I go. Huh? I know 9? You know 9. Well, that's my daughter, for Christ's sake, and she's bound to say this. Competitive. Yeah, well, okay, I know 6, actually. I'm trying to be cute here. 22,000, actually, to recite 22,000, it takes 24 hours. Sounds like yes, but try counting to 22,000 and have it right. They found that there are crazy people, my brother is one of them, by the way, that you tell them, 1,800 divided by 12 multiplied by 65, the square root of 5, and he goes, I got it. And they don't know how it's done. It's being done here, there's no doubt. They can read it for some reason. We have no idea why. But if these people existed today, then there is no reason why they didn't exist in the past. There were Einsteins, Newtons, Savants, all the time. We picked up about 100 of them these days. They think there is many more. Many perhaps in this room, because there is lower levels of this, what they call Asperger's disease. It's not a disease, it's a disability. It's actually very frightening. So people don't know how they do it. I mean, Daniel Tammet says he gets it from images of colors. But the odd thing is this, and bear this in mind, because this is where we get to the pyramids, because you're wondering what the hell has this got to do with the pyramids. The odd thing is that the numbers that they deal with, have you read Born on a Blue Day, you guys? Should read it. It's Daniel Tammet's book. The numbers that come in their mind all the time are prime numbers. Prime numbers. Now, I want to tell you what they are, but you remember the film Contact? Okay, I'll talk about this later, because this is getting really weird, because suddenly, when you get into this, when you get entangled in all this stuff that's going on, and cosmology and savant scientists, and then you hit prime numbers, you wake up, if you have done the studies I've done, because the Great Pyramid speaks with prime numbers. And this is the odd thing. You've got a monument, there's this pulsating mathematics that shouldn't be there. So you can see where we're going with all this. Computer. Now, we need computers to do all this. The computer isn't as smart as we are, but it is faster. That's the only difference. It's faster. It is faster consciously. You to do a calculation by hand, it will take you hours, where this thing takes a fraction of a second. But what goes on in your mind unconsciously, this thing will take days. To calculate pi, they've now got it to I think, 3 trillion decimal places. They took 1,000 computers in parallel, and it took 70 days running 1,000 computers in parallel. And this guy gets it like that. It is spooky. And I don't know if I'm passing the message here. You're all endowed with this. You all have it. It's on your shoulders. You are gifted with the most extraordinary thing in this universe, as far as we know. And it's this awareness. It's this awareness that we are so fantastic that we can do this unconsciously. Unconsciously. It's a universe being run by you unconsciously, inside. And that's where quantum mechanics comes in, because we're going to get to atoms. It's running how atoms work and how atoms behave. And there could be another universe as well. I don't know how, anybody my age, I'm 68 years old here, anybody above 60? Just one? Come on, that's math. I know your age. Well, I'm saying this because I was born in the days where, forget it, we didn't even know computers existed. I was born in 1948. In fact, they were just invented. The little machine that you run your phone here has 23,000 times the power that NASA used to send people on the moon. You had it in your hands. That's the progress. You remember we had the Nintendo and all this stuff, and look what you do with computers today. They are doubling in power and capacity and memory every 18 months, they say. In 5 years' time, this, whatever you hold, your iPods, your iPads, your laptops, will be prehistoric. We'll be laughing at this stuff. Like today, your kids, who have all this stuff, and you tell them, I had fax. You say, what is fax? I mean, who are the 6-year-olds? I was born even before the fax. I was born, in fact, we didn't have a phone at home. And that is only 60 years. In 1,000 years from now. In 10,000 years from now. Okay. The universe. I'm not going to go too much in that, and I don't want to do a course in cosmology, but okay, very, very quickly, this is a nice sort of diagram showing you the expansion of the universe, but what I want to do here is this. Something happened, we have no idea, they call it the Big Bang. We think, there's still a lot of arguments over the Big Bang, as you know, but an infinitesimally small, absolutely unimaginably tiny, inconceivably compact exploded. What was before it? Nobody knows. And it blew in such a speed, apparently 10 to the minus 37 seconds. It's like a fraction of a fraction of a fraction of decimal points of a second. It blew itself up. And then it started. And it created within something like a few seconds, and we're going here, I mean, there's one star, and the stars develop. I'm going to go at the end, I don't want to go through the whole process. Today we know, and amazingly, this is hardly 200 years after Copernicus, 400 years after Copernicus and Galileo. Today we know that not only there are other planets in our solar system, we know that there are stars outside there, all these little dots you see, in our own galactic system, the Milky Way. They estimate them anything between 100 billion to 400 billion. They're very rough figures because we don't know for sure. But 100 billion is enough. That's plenty of stars. But until the 1940s, until Hubble came, we thought there was only one galaxy. In fact, you want to see it? It's very simple. You go in the desert or up at sea and you see this white band that we call the Milky Way. That's your galaxy. You're looking at it from the edge. And we're right like a little corner of it, about 2/3 from the edge. There's a star, which is our sun, and we're a little planet going around this star. Until the 1940s, all this was fine. Until Hubble came along, and I'm not going to go into the physics of this, but they discovered that, wait a minute, there are other galaxies there. It isn't just our own. We now know that there is about 100 billion to about 500 billion galaxy, whatever estimate. 100 billion, let's take the low estimate. So there's 100 billion stars in our galaxy, and then there are 100 billion galaxies out there with probably an average of a similar stars. The number, they estimated very roughly as 10 to the 27th. Don't try and count it, you'll fill zeros all the way up to Mayfair. There isn't enough grain of sand on all the beaches of the world to match the number of stars that are in all these galaxies. So today, contrary to what was being said 30 years ago, it's totally arrogant, absolutely arrogant to think that in all this amazing, and the distances, we have a galaxy that we've picked up a few months ago that are 13 billion light years away. Speed of light, 300,000 kilometers an hour, a second. The light that is coming out from this beam here, it's gone in 1 second 18 times around the Earth. In 1 second. Can you imagine 1 year? The distance, and we're calling it 13 billion years, 13 billion light years. It's so incredibly vast. There has to be other things out there, there's no doubt. You will not find any physicist today, any cosmologist, who will tell you the contrary. It's totally unclear. We haven't found it yet, but to think that there isn't is now considered absurd. More absurd because we're finding planets in our own galaxy. In a little spot, and I'm going to get there because I know Andy is very much into this now, the Lyra Cygnus region. Yep. Okay, we'll get into that. So here is cosmology. We have to consider, we're obliged to consider that we're not the only ones here. The question is, what adds to this? And that's where panspermia comes into play. Because we know now, and it's a fact, it's not theory this, we know now that you and me, and sitting there, and this lady is here, and the chair, and this computer, and my genes, is all made from atoms, elements. And these elements have come from a star that exploded somewhere in our galaxy. You're made of star stuff. You are star material. You're star ash, become alive and conscious. That's what you are. Which star? Yeah? Maybe many stars. There are atoms in you that were constructed 13 billion years ago and went through galaxies and other stars and finally came to you. Panspermia says, oh, here is the galaxy. Nobody can see it from the outside. We can only see it from the inside, this Milky Way, as we call it. But we put where the sun is roughly on the edge, about 1/3 from the edge. Just one star among a billion. Your sun is a star, of course. We now know two things. We now know that there are other stars within our galactic system, nearby stars in terms of cosmic distances, of which there are planets. We now know for sure. They've picked up about 4,000. Two of which, the famous Andromeda B and forgot the other name, two of which are Earth-like. And that is only since we put Hubble telescope out there in 2009. They're going to find billions, they think. I'll get into that because it's only looking at a small little region, surprisingly at the region where you're going to hear Andy talk about the Cygnus Lyra region. They're looking because they can't afford to move throughout the galaxy. It's very complicated, so they're aiming at one spot. By the way, the spot that was picked up in the story of Contact, and there are reasons for that. The book was not just fiction. Near the Vega region, Lyra, Cygnus, Vega. And so far in this, literally, it's a bit like going in Hyde Park, you know the size of Hyde Park, and looking at 2 millimeters of ground and saying, oh, there is blades of grass there. That's all there is. Whereas you know that there is a whole park full of grass. So they've picked up 3,000, 4,000 planets on a very small spot in our galaxy. By extrapolating, they're now concluding that there must be billions and billions of planets out there. It's impossible. It's impossible that there aren't planets which are similar to ours. There's got to be. You know the famous Goldilocks band. Okay, you keep shaking your head. You know a lot about this, man. But the Goldilocks is that it doesn't have to be too hot or too cold. You know, the porridge? Huh? Well, it has to be, we assume life as we know it. Well, our planet happens to have life because we're just at the right spot, the right distance from the sun. If we're too close, we're like Mercury, we all melt. Too far away, it's too cold. So it has to be within a band, and we call this the Goldilocks band. But we're finding these planets in the Goldilocks band of other stars. Now, sure, they're in the right place, but do they have life? And Panspermia comes into it. Panspermia says that we know it came from another star, these elements. Well, if it came from another star here, why did it go on another planet there? How did it come here, by the way? Well, it comes when a star gets too fat. I'm using simple language. It's supernova. It gets too big for its own good, and the gravity pulls it in, and the force of gravity is such that it produces two things. Enormous heat within the star, enormous heat within it that it binds simple atoms like helium and hydrogen and creates the heavy atoms of which you're made, iron, phosphorus, and all this stuff. And then it explodes. And it spews out this material, and it's picked up by comets, by bits and pieces, and finally hits a planet. And it takes about 4 billion years, because we know our planet is about 4 billion, to reach you and make this brain. A bit of star came here, and it took 4.5 billion years to make you. But the universe is 14 billion years old. We're newcomers here. We're still about a third of the distance, the time distance. What happened before? If this supernovas were occurring for billions of years before, what if they did this on another planet? It's a what if that we have to consider because the odds are extremely high. So there could be people like us, or life like us, that is billions of years older. Can you imagine talking to a primitive caveman just about 14,000 years ago? Telling him we have computers and we have laptops, and he wouldn't even understand. I mean, he wouldn't even be near you. Can you imagine somebody on the other side having 1 billion years advanced coming to tell you who they are? It's completely out of our range. In fact, they probably wouldn't be interested in us sometimes. It's like talking to a slug. I mean, we're having a conversation with a slug. Yeah, not interesting. I'm trying to impress on you that what was considered crazy and nuts and people calling you pseudoscientists is no more this. Because we have reached that stage where all this is possible. We haven't proved it yet, but it's all possible and we have to open the possibilities. And I'm going to look at my watch. Oh, good. Okay, here is Hubble. I'm going to move fast here. Here is the famous Mount. That's where he found that there were other galaxies. We'll move around. And now we have the Hubble telescope, which before that, we couldn't even count those galaxies. We knew there were many, and that's what enabled us to do. It's sending you pictures. They look lovely stuff, by the way. And then the Kepler Space Telescope, and that's the interesting one. Kepler Space was put in action, let me get this down, 2010. Kepler is done by SETI. SETI is the extraterrestrial search. It's being funded privately. It was funded by the US government a few years ago, but now it's been funded by big shots like Microsoft and people who have a lot of billions. And they've sent this telescope, which is a photosensitive telescope. It can actually read and convert into images and see the planets. They actually managed to see them, and it's a bit complicated to explain this. And that is why, since only 4 or 5 years ago, we've managed to discover, totally unexpectedly, that it's full of them out there. It's loaded with them out there. Many, many, many planets. And we're a planet. So that's it. We have to be open to this possibility that there is not just other life there, but Panspermia says maybe life that developed long before us. Long before us. That's one possibility. One possibility. Yeah, well, there we are. That's a little region, by the way. There is a Milky Way. Do you see it? Sorry. Does it show there, the band? The Milky Way, and here is where the Kepler telescope is looking at, in this region here, the Cygnus-Vega-Lyra region. It's just a little spot, and they already found 4,000 planets there, of which many are possible Earth planets, 2 of which are extremely promising. All this has not yet been explored. It's credible that we are this generation that's beginning to know this. 20 years ago we didn't. We thought there were, but now we know. And that changes everything. It changes everything because we have to consider possibilities that we're afraid to consider, or at least I was. Here is, by the way, Proxima b is the most promising one. There it is. This is an artist's representation. It doesn't look like this in pictures, but it is there. It is in the Goldilocks. It is the size of the Earth, and they're picking up things that suggest life. Now, Sir Isaac Newton. Sir Isaac Newton? We all know Sir Isaac Newton, no? Please tell me you know him. Sir Isaac Newton. You know the story, the famous legend, the apple falls on his head and all this stuff? Well, apples have been falling, right? Before him. And bananas. And coconuts, if you live in the tropic. And oranges, and stones, and bricks. Nobody wondered, maybe they did, but he's the first one to say, well, why is it falling down? I mean, what's pulling it? And the thought. Luckily for us, the man who had the thought happened to be the professor of astronomy and mathematics at Oxford. Or Cambridge, is it? Oxford? And he could speak. But he still was missing something. He needed calculus. Today, the reason we have put people on the moon is because of this man. Fantastic. We're all very happy. It works fine. Calculations, beautifully. They can land a spacecraft on Mars. They even can direct it. They can tell you where if they, unfortunately, all these wars are going on, but if you toss something like a bomb, they know exactly where it's going to land. Because of the calculations of the laws of motions and the laws of planetary motion, the laws of gravity. Then comes Einstein. And he refines them. He comes with this famous EMC square, the famous general law of relativity. I'm not going into that, but that refined the gravitational laws. Everything was fine, everybody was happy, and the physicists were happy, and we all went home, and nobody worried about it. You know, we let the physicists calculate, and they tell us they can send people on the moon, and we're there in '69, at least we were. You know, it was all lovely, and everybody knows how the universe works, and we can calculate it. Unfortunately, or fortunately, depends how you want to see it, comes this man and various others, and they discover quantum mechanics. And suddenly everybody's baffled. Everybody is baffled. And I'm not going to go too much into it, but quantum mechanics is about the study of atomic and subatomic particles. You are made of subatomic particles. I can even give you a rough figure. There's 10 to the 27th, roughly, atoms floating in your body, doing all sorts of weird stuff as you're sitting here. Your brain is made of subatomic particles. We get down to the fundamentals here. Newtonian and Einsteinian physics just stopped at the atom. Everything works very fine there. Quantum mechanics works in such a different way that they're totally contradicting each other, and yet they're made from the same stuff, except that there's a barrier. The minute you exceed a certain size, you get into Einsteinian, Newtonian mechanics. It works very well, and send people on the moon. The minute you go below that barrier, that limit, you get subatomic. These things don't work at all like that. In fact, they work in such a weird way that, as I was saying, I don't want to go into the split experiments and all this. Very fast, I'll pass through them. But basically, it opens up because it is true. It is true that atoms and subatomic particles behave in the weirdest of ways. You can take a photon or an electron and pass it through the famous slit experiment, and suddenly it's in two places at the same time, and then suddenly it will be in an infinite place. It's the probability. You, as you're sitting here, all is fine because you are big. They have atoms that have conglomerated each other. They make up your brain and your feet and your blood and all this stuff, and it works fine. If I could reduce myself to smaller and smaller and smaller and smaller, if I could be the size of an atom, I wouldn't see you at all. I wouldn't see Andreas Smet at all. In fact, I would see nothing, because you're 99 empty space, believe it or not. Because when you get to that level, these atoms are so far away from each other that mostly it's empty space, like space. Like our planet is 92 million kilometers from the sun. Empty space, most of it. But these things that are in there in this empty space behave very weirdly. They could be here and they could be there, they could be in another world, they could be in another universe at the same time. More even weirdly, they could be on the other side of the universe, and as he moves his atoms or his hand to the left, some of his atoms twist around and they move atoms on the other side of the universe, maybe in another galaxy, in the same way. Weird. As you know, I know the famous phrase, Einstein called it spooky science. He refused to accept it until experimentally it was shown to exist. It exists, except we just don't know it. I mean, we can't understand it. It's too weird for us. Too weird for us that you're sitting here and it could be you in another world sitting at the same place. With an infinite number of possibilities. You've got a blue shirt, there's a green shirt, and you cross legs, and there is not cross legs. You're alive here, you're dead there. It's totally mad. But it's true. So we have to enter a different form of thinking. The thing where, look, I mean, we have to think of something else here. And that's where the most extraordinary theories have come out, and that is where it forces people to consider, because while all this is happening, this is matter, this is physical matter, there is awareness, there is consciousness in him as well, which is also made from the same stuff. And we get into this, well, how can something that is not matter, a thought, an idea, an imagination, it's not physical, I can't touch it, and yet it's working in there. And that's where you start talking soul, you start talking spirit, you start talking consciousness. And it frightens some of the scientists. I've had talks with them, but they have to, and you'll be very pleased, at least one of them, and there's a few, but one of them has come out openly. It's been a book that I've just finished. Dr. Chandra Vikramasinghe is saying, look, I'm sorry, I'm not going to like this because you didn't like my panspermia. Now it's becoming kosher. They do television programs now every day about the panspermia. I think it's designed. I have to go to the simple explanation here. Somebody designed this. Not just because of this, but because you and me and everything else in the computer and everything in this room and elsewhere in London and in the whole universe exists because there are 4 fundamental laws that hold this together. Gravity, electromagnetism, the strong and the weak, nuclear forces. The strong one holds the atom together, and the weak one is gravity, by the way. As you jump, I mean, it's fairly weak, by the way. In other words, you crash on the ground. You tweak one of them, one of the four, by the most minute fraction, and this universe disappears. It's incredible. It's almost impossible to imagine that four forces came up with a very precise combination to make this universe. So there's two explanations. Pick the one you like. Either there's an infinite number of them, and we happen to be the one that works, or the others don't work, or somebody designed it. Something designed it. And then we're almost talking about creation here. We're getting near there. And we have a scientist, and many following him now, who's actually putting this in black and white in a book. After 60 years of studying quantum mechanics, astrophysics, cosmology, astrobiology, he finally comes to the most simple explanation. I've come up with all sorts of theories and possibilities and string theories and all this stuff, but why don't we go for the most obvious one? This thing is designed. And we now, science is just at the frontier now of spirituality, of a new religion that is dawning on us. A religion that is, I would call it a natural religion. It is based on knowledge, gnosis, old religion, not on inventions and patriarchs' ideas and virgin births and all this stuff. This is hopefully going to be, and this is why it's so important to get into this. Get into this. Okay, again, like I said, I don't suggest we all become geniuses in mathematics, but to get updated, because that is where it's going on. And the marriage of science and spirituality. Now let's get to the pyramid, all right? Because you want to hear about the pyramid or not? Yes? I don't have much time. They're going to throw me off stage. The bell is going to ring here. So we've done that. Okay, this is entanglement. This is lovely. I'm not going to go into that. You've heard it. There's Einstein saying spooky. Does he say spooky? No, there he is. Spooky. Hello, on this? All right. This is, well, I mean, if you're worried about not understanding, here is Richard Feynman, one of the founders, saying, people don't get it to this day. Nobody understands it. They can calculate it and tell you exactly what an electron is going to work. Somebody sends a message, you pick up your phone, it rings, and you go click, and it's, oh, hi. What's happened is that photons were sent from, God knows where it's calling you, went to a cell, it came down in nanometers of a second and reaches your phone. That's what this thing does, and nobody knows how it's doing it. We can calculate it. But who says he understands? Everybody's saying you're either crazy or lying. Nobody gets it. So don't worry if you don't get it. Nobody gets it. But it's true. They've actually proved, this is the test, I'm going to go fast, but in Tenerife, actually, as we're sitting here, they've actually proved what they call entanglement, that one of your subatomic particles that is entangled with another one can spin in one direction, and the other spins in the other, anywhere in the universe. They've actually got a photon transmitter, which you see one of the pictures there in Tenerife Island, and they've sent it 140 kilometers. They managed to send one electron, and they twisted it, and the other one, damn it, twists on the other side. They don't know how it does it. It works. It's baffling. And it does it instantaneously, not even the speed of light. It's instantaneous. That means you can be on the other side of the universe, and it's instantaneous. As I'm speaking here, boing, it's happening on the other side. There is no physics that can explain it. All we can do is calculate it. There is no logic that can explain it. It's beyond us. Maybe we're not evolved enough, I don't know. There, that's the island. Well, I've got pictures of what they imagine to be the multiverse and universe. You've heard it all there. The Matrix. They begin to talk about the possibility even that we are a simulated universe, for God's sake. Or we're a simulated of another simulated universe. It sounds crazy, but you've got Nobel Prize winners talking about this. Maybe we're a computer game, I mean, God forbid it, but these are possibilities that we have to enter because they are possibilities. Now, what I'm saying is maybe the pyramids are simulated. Or maybe we are simulating something else, I don't know. The reason we believe that is not because of all we know about quantum mechanics, it's because we'll be able to do it in about 20 years' time. As I was saying, look at what's happening with computer power. Look at the simulated games that kids play today. They're so sophisticated that 40 years ago, when we had Super Mario jumping around, they can do war games and all sorts of stuff. I mean, frightening stuff. And that is nothing, absolutely nothing of what's going to be in 20 years' time. We'll be able to simulate you somewhere else, and you're going to look at, sorry, I'm pointing at you. Okay, sorry, it's not you. I'm going to pick you. I'll put you in another room. It's not you, but they'll believe it's you. That's how good it's going to be. And many ethical questions to ask here, but it is physically, theoretically, technologically possible. There's a book that you should read, if you think, yeah, it's available now, it came out a few months ago. It's called The Future of the Mind. Michio Kaku wrote it. Written for people like us to understand it. Read it. Be surprised what's going on in research today. People trying to create artificial brains, robotics, artificial intelligence, all this stuff. Okay, that's one possibility. And the brain. I spoke enough about the brain, but here is some weird stuff. Let me give you a few statistics and then just to tell you what's going on there. There is an estimated of 100 billion neurons there. 100 billion nerve cells firing at the rate of 50 impulses a second as we are talking. And you're just sitting here and I'm up here. And I don't know it's doing that. But to link up and make your thoughts and ideas and calculations, it's called a network. It's called a network. They call them synapses. And they're linked with like wires, if you like. There's 160 kilometers of these wires in there. It is so complex that today, with all the neurological studies they do, they've only managed to just about understand about 4 or 5 neurons in the brain of a rat. To understand your brain, and there is brain projects going on in Switzerland and America, funded by billions, to charter your brain. It's frighteningly complex, but they think they'll be able to do it maybe in 30 years' time, 40 years' time, 100 years' time. They'll do it. That means you'll have to have a computer which is equivalent to your brain. You'll have to have your brain is not a computer, by the way. It's wrong to say this. It doesn't work as a computer. It works as a biological processor. It's more sophisticated than a computer. In fact, we will have computers that work like your brains if we can make them work biologically. We're talking about molecule computers. We're talking about quantum computers. These are the future generation. Your kids, well, my kids are grown up. Your kids, from these, when they're 20 years old, will be playing with quantum computers at their home. Today, quantum computer is the size of, this room. Very complex and it's very basic. But like computers were 40 years ago, the ones you hold in your hand. We'll do it. They'll be able to create an artificial machine that is the capacity, but here's the other problem. They have to program it. And that is another story. That is another story. You'd have to tell it how to, sorry?
Please don't tell it. You've got 5 minutes left.
Oh, bloody hell. I'm enjoying this. Huh? You're having fun with this?
We came to hear about the pyramid.
Yeah, pyramid, huh?
Yeah.
Well, I'm going to go fast. I'm not going to bother with this. You've heard much of it. By the way, here is the primitive computer, 1940. Look how it looks like. The thing you hold in your hand. There you go. Apparently ladies operated it. They had all these secretaries plugging in things and putting in things. That's a computer. And that's today. That is the supercomputers that are coming in. Look, they're 80 meters long. That's in China, the latest one. They have a bigger one, which came in 2006. It has 41,000 processors. You know how many processors you have there in the equivalent? 82,000. You have twice the capacity of this computer there, which today is the biggest, fastest, strongest computer you can imagine. And you have more processors in there. I really want you to think about it. We're so extraordinary, each one of you. Each one of you is a marvelous thing. To simulate 1 second of a brain activity takes 82. Right, let me move. You want to get to the pyramids first. All right, I'm moving fast here. All right, I'm going to move very fast because I'm not going to do mathematics and I have 5 minutes. Can you give me another extra 5?
20 minutes.
Huh? How much do I have?
You finish at 6:15 for this.
Finish at 6:15.
Yeah. Everybody looks at the agenda.
We have 20 minutes.
It was supposed to be an hour.
Yeah, well, let's break some rules, huh? Yeah. Coincidence pigeons. We get to the fun stuff here. Very quickly. I was in Milan around Christmas time, and they asked me to give a talk near the Duomo. And it happened to be in a book shop where there was a lot of pigeons, like Trafalgar Square, flying all over the place. And I thought I'm going to play a thought experiment with the crowd, just to have fun, like I'm having fun with you. And I said, I had a table in front of me. I said, what if a pigeon comes and lands on this table? And they said, well, coincidence. Yeah, I said, there's a lot of pigeons out there. They never had it before, but I said, well, it's bound to happen one day. But then I said, what if another one comes? So about half of them said, well, it's a bit odd, I have to admit. And what if a third one comes? And what if a fourth one comes? And what if a fifth one comes? By the time I got to the seventh, they began to say, I think there was 2 people in a crowd like this who said, still a coincidence. The majority said, no, it must be something else. Maybe they're trained pigeons. Maybe they're simulated pigeons. They began to think of another possibility, because at what point do you stop saying coincidence? How many pigeons will it take? I gave a talk to this in America, and they began going around. They said, are you a 2-pigeon or 3-pigeon person? The majority were 2, by the way, in America. There were 3 pigeons, 4 pigeons, 5 pigeons. There are some that, no matter how many pigeons you poke, they still say coincidence. The Egyptologists, for example. So I'm going to show you pigeons, metaphorically, with the pyramid. And we're going to see where we stop. Right? So, here we go. Well, you know the Giza necropolis, 3 pyramids. 1 big, 2 big, 1 small, offset. Here's the other one. We know now there's always been a mistake about studying this monument. Now I'm a construction engineer, I should have said this from the beginning. I actually trained in England here. My brother is an architect. They've been studying the pyramid and measuring the pyramid. Yeah, it's good. But it isn't what is there. It's very eroded, by the way. It's what was it designed. So you get an architect's plan, it gives you dimensions. But there's always a tolerance. And after 5,000 years, you're bound to lose a few centimeters here, a few centimeters there, or a meter there. The design has been recognized. We know that this pyramid has a base of 440, what we call royal cubits. We are sure of this. Egyptologists are sure. There's no question. And we know that it has a height of 280 royal cubits. What's a royal cubit? Well, 1 royal cubit is about, no, exactly, 0.5236 meters. Right? About half a meter. But very precisely, 0.5236. Now here's the first pigeon. Where is pigeon? Ah, there it is. Well, coincidence. The base, square base of the pyramid, in relation to its height, the ratio between the height and the base is the same as the radius to a circle. In other words, you can convert the base of the pyramid into a circle. It's called squaring the circle, if you like. It's a fact. But it might be a coincidence. It just shows this dimension, and whoop, we have a pigeon. It's a good pigeon, but it could be a coincidence pigeon. But here is the odd one here. You take the height, and you take half the base, because we got the ratio of the height, which is the radius of a circle. And when you find the relationship of this triangle. You see it at the top there? It's a simple Pythagorean triangle. When you take the height of the pyramid with half its base, you get a dimension that is universal. It gives you what they know as the phi dimension, the golden ratio they call it, the golden number. It's 1.618. It's dimensionless. It's dimensionless, it doesn't matter what dimension is, whether you use meters, whether you use feet, or whether you use apples. And that is universal. All these dimensionless constants, if you have this number and this number, it will always produce this constant. It's a fact. But that's not a pigeon. It's a kind of interesting pigeon. The interesting pigeon is below. Because here is the weird one. Remember the circle? If you take a circle, a dimensionless circle, and you give it a unit of 1, that means the diameter has a unit of 1. Right? You have a circle, and the diameter is 1. 1 meter, 1 foot, 1 centimeter, 1 kilometer, 1. Unit 1. And you divide the circumference. Circumference is bound to be it's bound to be pi. I don't know if you remember in mathematics. It's bound to be pi, which is 3.142, roughly. More precisely, at 4 decimal places, 3.14159, and she has 9 more, I don't know. All right? But it's good enough. Up to 5 decimal points, we can calculate rockets. To work nanotechnology, like getting things in your body and medical instruments, we have to go to about 39 decimals because they're made of round things and all this. We don't need 3,000. But you'll understand why it's interesting to go infinite. I'll tell you in a minute. But here you are. So if you divide this circle, which is 3.5, well, you don't have a machine, divided by 6, it gives you the royal cubit. Gives you the royal cubit. It's interesting. We've known this for a long time. It would be a coincidence. It's one of those odd things. It's too precise, but hey, it's interesting because they're telling us, look at the circle, pyramid, circle, and we're going to unit. Play with this unit a bit, and boy, we divide by 6, and we get the royal cubit in a circle. Comes out. It's a fact. You can try it on your machine. You have a calculator. Divide pi by 6, and you get the royal cubit. In non-dimensions. However, so it's a number. You get 0.5236. You get that. But it's neither in meters, neither in inches, it's non-dimension. Now give it a dimension. If the diameter of the circle, unit 1, is 1 meter, then you get the royal cubit exactly how it is. It's 0.5236. You understand this so far? I'm not losing you with maths. Now this is interesting. Because if this is true, if somehow they used the unit of what we call a meter, then it's a problem. Because to know the meter, you have to know the dimension of the planet. Can't be done otherwise. Now we know that the French did it in the Napoleonic era in 1793, if you're interested. They actually measured a longitude from, I think, the Channel Island, the Channel Sea, I think Dunkirk all the way to Barcelona. It's about 1,000 kilometers, and they knew the distance. With simple trigonometry, they worked out the circumference of the Earth was a certain dimension, and they said, we're going to take 1/10,000,000th of this dimension. They came up with a meter. The meter is 1/10,000,000th of the circumference of the planet. So, it suggests, but we can't prove it yet, that, boy, if they had that unit, that meant they measured, these people who did this pyramid, knew the circumference of the planet. But, so far, we haven't, it's a nice pigeon, but it's not, it's still a semi-coincidence, it's kind of bizarre. We want to find something in the pyramid itself. In the pyramid itself, we can actually see it, or at least know it's there. That is a circle with a diameter of 1 meter, right? We want to find one to see if this is correct. Now, I've been in this damn pyramid, I don't know how many times. I've climbed it, I went inside, and I can tell you there is no circle there. There is no circle that I ever saw. In fact, there's no circles in the pyramid. There is the calculated circle on the base, but there's no circles. Have you seen circles? You've been in the pyramid? No circles. Until my annoying brother comes along. An older brother who is one of these strange savant mathematicians, an architect as well. And let me show you. So pigeon number 2, but number 3 now. Huh? Because of this. It may surprise you, or maybe you know this, that the pyramid, we always say it's four-sided, but no, it's not four-sided. It's actually got what we call a concavity in the middle. It's basically 8-sided pyramid. Egyptologists don't talk much about it because they don't know what it really means, and on top of that, they come up with silly ideas like it's a builder's mistake, except we've got the concavity on 4 sides. It's too precise to be an error. It seems to be a deliberate design. And here comes the architect. The architect says, okay, let me design this pyramid again with this concavity. Let's see what I get. Because when you go at Giza today, how many have you, I can't see you. Who's been to Giza, just by curiosity? 20%? Okay, you probably have noticed that the pyramid is truncated, it doesn't have a top, right? And we've always assumed that it had an apex. But if you design it again, what we call reverse engineering, we go back to the fundamentals and we redesign it again. Surprisingly, I can tell you this, I'm not going to go in details, that architects today, and it isn't just my brother, he's a very good architect, but we have architects in Spain, we have architects in America who are into this, and they're all surprised that if you're going to redesign this pyramid today, with all its internal system, we're going to go there, you're going to need a computer. It's too complex for an architect to decide by hand. I know I'm going to say take my word for it, but you'll be reading a book about this. But even so, where is this damn circle? Because if you redesign the pyramid with this concavity, you're obliged to have a truncated top. It's not going to go higher. The geometry of the concavity forces it to stop at a certain level. Forces it to stop. And then came this idea to this nutty brother of mine. I'd like to bring him here one day, he's going to puzzle you. I'm not going to go into maths here. What comes out of all this is a virtual space. There is a truncated top, and if you extend the edges, you get a virtual space. Many architects have baffled of this virtual space because, in this case, in this design, you can fit a sphere or a circle inside there. And lo and behold, the sphere that you fit in there, or the circle, has a diameter of exactly 1 meter. There's a fact. We've got to recognize, maybe it's another coincidence, that they could only know it if they know the dimension of the planet. How the hell could they do it? Who are we talking about here? And then you start thinking, my God, maybe it isn't what we think it is. I'm going to go up to 10 pigeons here, and then hopefully where you're going to stop. Circle, meter, dimension of the planet. And then what you find is if you take the perimeter of the base in meters, or in feet if you like, but I'm taking it in meters, it's 921 meters, 0.53, check it, all right? It's a fact. I'm giving you facts here, I'm not giving you theory. So if you divide by this by 2, you get 1,843.06 meters. It's a fact. And here's the weird one, right? You increase it by the power of 1,000, you increase it by 1,000, and you get 1,843 exact kilometers. There you are, the nearest decimal. And it gives us exactly 1 minute of 1 degree of the Earth planet. It is a geodetic measurement. It's precise. It's not if, it's not half, it's not a quarter. It is precise. The base of the pyramid has incorporated in it, in this design circle, in this strange virtual reality, the geodetic value of a degree. And strange enough, I don't know if you know this, because the Earth is curved, this 1,843 kilometers is precisely at the equator. If you measure the same amount, distance, at various parts going to the pole, it increases very slightly because of the curvature of the Earth. It is precisely at the equator. This monument, at least mathematically, is saying my base and my height, in fact, my model, is a reduced model of the planet. It is a fact, whether it's a coincidence or not. It is a mathematical fact. Whether it is a coincidence is another matter, but let's go to more pigeons. I'm going to take you up to 10. I hope you're going to stop at 6, but right? The interior of the pyramid. It's extremely complex. That is why the architect tells you. Because it looks very simple. You always see these drawings and, you know, in the Egyptological book, and it looks like they cut a tunnel here and they went up there, but no. Remember Rudolf Gantenbrink, the man who found the door? The famous door at the end of the shaft, the Queen's shaft? Yeah, come on. Well, Gantenbrink is one of these nuts in computers, and he redesigned the pyramid. And he discovered, here's the weird thing. Now, architects, well, today they do a lot of stuff on computers. Architects would open a plan. You remember when you were at school or at your home and you did drawings and you would draw on a sheet that had grids and little squares, so you could draw a line. Architects do this. Well, they used to do this until they messed around with computers. So they would have a sheet and they would grid it, either in feet or in inches. This pyramid was designed on a grid. It's a fact. It's proved. Because all the points, I'm just showing a few here, sorry, fall on specific points on the grid, and lo and behold, this grid, the little squares, well, it's much bigger than this, is 11 by 11 royal cubits. 11, the grid is little squares there. Am I showing it here? Yeah, you see the grid? Each little square there, of course, it's much bigger than that, is 11 by 11 royal cubits. That gets you thinking. Because 11 is one of these annoying numbers. It is a prime number, and it's a very special prime number. I'm going to go through this. And it's designed on this basis. Why the hell would an ancient, primitive designer do this design and come up with a base of prime numbers? What are prime numbers? Well, a prime number, very simply, is a number that only divides by itself. Like 5. Like 2. And bigger numbers like 11. Give me another one. And they are infinite. They managed to sort of calculate, I think, 3 billion of them, and it goes. And here is the weird thing about this prime number. They do weird stuff. Because hidden behind the numbers, so we get the language of the universe. We call this factorizing the prime. Factorizing is integer. Integer is a non-prime number, a full number, like 14. It divides by 7. 2 times, right? But when you divide it by 7 2 times, you get 2 prime numbers, 2 and 7. When you divide any integer is a full number. You know, it's 69, 68 years old, that's an integer. It happens to be prime number as well. If you factorize it, you find what multiplies it to get the same thing, you always arrive at prime numbers. It is one of these weird things. They can't understand it. There's in mathematics going into all these crazy fields like the Riemann theory. You see the film, by the way, The Man Who Knew Infinity? No. I'm going to buy the DVD, go and see it. Buy DVD. Ramanujan, no? No. Okay, they're always playing. It's, oh God, I don't have time for this. G.H. Hardy, a mathematician who introduced pure mathematics in this country at Cambridge University in the 1920s, was contacted by this young Indian who worked as a clerk in the in the port of, my God, I forgot the name. Mumbai, maybe, you know. Madras, actually, it was. And he sent him a letter, and this guy worked out the most incredible theorems. He was just a young man, hadn't even schooled in mathematics. They brought him to Cambridge. He produced a formula that could solve a problem that hasn't been solved to this day, but at least he produced a formula, the famous Riemann theorem. Nobody has produced it. It's the most bizarre theorem. You got the biggest brain, they're offering $1 million. If you're good at mathematics, you can solve, they give you $1 million. Even Einstein could not solve it. And this guy produced a formula out of his mind, and he kept insisting that he got the information from a goddess. Go and see the film, it's incredible. I'm surprised you haven't seen it. Wolfgang Pauli, the Nobel Prize winner, who was the father of quantum mechanics. He used to say they get this in dreams. He worked with Carl Jung. Carl Jung developed the theory of synchronicity and the universal consciousness based on quantum mechanics. He was convinced that he got this in dreams. This guy worked out the spin. He worked out the spin of atoms. He got a Nobel Prize for it. He's not joking. Because it's happening in there, and they could read it through the mathematics. They could speak the language. Now, honestly, you have to see this. Read the story of Rabban It's funny. G.H. Hardy, who is the mathematician, astronomer, brought him to England. He's played by Jeremy Iron, no? Brought him over. G.H. Hardy was the professor of the father of Chandra Wickramasinghe, who I'm writing a book with. That's why I'm into all this stuff, because my God, I didn't know all this. It brings us to the pyramid. So here we are, prime numbers. And we get prime numbers. If you square 11 times 11, you get what? 121. 121, right? It's very simple. 11 times 11, 121. We're finding this in the design of shafts and positions. We move forward. The chamber of the King's Pyramid is offset from the center. Nobody understands it why. Mathematicians, architects have worked out that along this grid, it's moved to 7 times 11 times 2 times 11. 7 times 11 from the base, 77, and 2 times 11, 22 from the distance of the center. He's using prime numbers. He's talking. There's a message here. There's a language, because you take the prime number, it isn't just a number, you factorize it, and then you understand what it means. He's saying 2 times 7 times 2 times. That is, remember the film Contact? The first sign of a civilization from somewhere else, talking to somewhere else, has to communicate with you initially in prime numbers, for you to know that there is a language. Then they teach you the language. They tell you 2 means this, and 5 means this, and 7 means this. The pyramid is doing that. Now, it's doing that by pigeons, coincidence, or it's doing that by something else. Let's move on, because what is it telling us? When King's Chamber, so not only we found that it's positioned, but oddly enough, when you convert this into meters, you come to 11 meters. They're using the meter again. They're telling you circumference of the Earth, I know it. Maybe it's a pigeon, I don't know. It's annoying me, because that's what it's doing. It's pulsating information in stone. Pigeon what now? I've lost count here. 9. I had the numbers on. I know. I put the numbers on mine. My daughter wouldn't do it for some reason. Here's the door. So lo and behold, remember the shaft. And when you get to measure the shaft, it's 11 times 11 from the base. And then they drill a hole in the door, and the first ever hieroglyphs they find in this pyramid, painted in red. Nobody could have put them there. It must be put by the rewriter. Damn it. Damn it. Here they are. 1, 20, and 100. It's the way that says 121. It's a code. It's a code. And I don't know if you, you might be tempted like I am. I'm rereading the book Contact that was already, the film is based on Carl Sagan's book Contact. Reread it now. Because you'll see in the film, if you watch the script, it's on YouTube now, the message comes in prime numbers. They begin to realize this is intelligent. 2, 5, 7, 11. It stops at 102. They're convinced now. That's it. Can't be artificial. Can't be fake. It can't be natural. It is constructed. It is intelligent, but it stops at 102. Damn it, the pyramid stops at 102. Or you know the shaft theory and this pointing to Orion and Sirius. There they are. Coincidence, number 11. Ah, it's good, it's from him. There is a little nebula here. I was telling you earlier. Okay, let's... I've introduced the pigeon factor. You're going to tell your friend 3 or 4. We think that we are made from stuff that came from this nebula. And they're pointing to it. Something are pointing to it. Okay, pigeon 11. This is the weird one. The second pyramid. And that's fact. Take the base, take the height, divide the height by the base, by the first prime number, and you get 137.03. What the hell is 137.03? Just Google it. It's a number that comes out of nowhere, out of mystery, when mathematicians do calculations with quantum mechanics, with cosmology, and this number pops out. They're obsessed. They don't know where it comes from. If we were to send the number 137, or the fraction of it, 137.03, whoever is up there knows that we know quantum mechanics. That's it. It's the first number that we would send with prime numbers. Send the prime numbers intelligent. Here's 103. You cannot know this number after having said, I know prime numbers, unless you know quantum mechanics. It's impossible. And you get it precisely to the second decimal place on the measurement of the second pyramid. And now, there's a fellow called Gary Osborne who found it with the same precision in the Great Pyramid. Contact. Are we dealing with contact? Oh, well, I can't move the slide here. Hello? Help? Ah, it's a slow one. That's actually from the film. It stops at 101. They're sure now. They're absolutely sure. So let's understand the language you're talking about. We need to understand what is the language. We know the mathematics. We know that they speak mathematics, the design of this pyramid. What is the language? I don't know it, but that's what we need to move ahead. Because, wait till you get to pigeon 14 and I'll stop there. Because then it tells us something really weird. Now here's the number pops up again. 2 prime numbers. You saw 101. The shaft in the north shaft stops at level 101, and the other stops at 103. 2 prime numbers, and they're very odd prime numbers. Or science here, but they're actually called Chen primes. It's the name of the Chinese guy who found it. If you take 1 prime number, 101, and you add 2 to it, you have another prime number, 103. It only works for certain numbers. This damn thing is intelligent. It's important. I know prime numbers, and I know how they work. You still don't say I'm. That's what's coming out of this. And believe me, I'm having a hard time. I spent 30 years not saying this. But time is saying. Counted for prime number. This is up to 1,000. I'm going to tell you what they do. It's the weird thing. Very quickly, right? If you take any integer, right? Let's start with 1. If you take 2 and divide it by 11, so 2 is a prime number, right? Just trust me, it's a prime number. It's the first prime number. Not 1, 2. 2 is the first prime number. Divide by 11, look what you get. You get 0.1818181818. You take prime number 3, you divide by 11, and you get 2.7, 2.7, 2. Are you getting my message? That's what this thing is saying. And you take prime number 11, then we go up the field, prime number 17, divided, you get 544, 544, 544. I'm talking to you. dummy. Not you. No, it's a tomb. No, it's a tomb. No, this is not a tomb. Whatever it is, it's not a tomb. And then they tell us in their text, the pyramid text, that what they want to do is to put a physical body there and transfer him to the stars. That's what they say they want to do. Well, the stones, I mean, how can you do this? Can't do it. No, of course you can't. Honestly, you can't. It is not a machine, but it could be the blueprint of a machine. We've got all the information here. Now wait till you have the technology. Because we do have the science to do this, believe it or not. We simply don't have the technology yet, but we are sure we're going to get, once we get those computers up to this level, once we get scanners and load your consciousness on a laser beam and send it to the stars. It can be done. We need the money. We need the technology, but it can be done. Whoever did this seems to know this. He doesn't have the technology. It's not there. Put a blueprint. That's my guess. It's wild. But bloody hell, we're now at 11, what is it, 12 pigeon? Where are we now? All right, let's go to, now here's the weirdest one. And that is the very difficult pigeon. And I'm going to stop here because they're going to scream at me. Pigeon 14. This pyramid is set on a specific spot. There's been a lot of arguments about this, and people call you mad and not mad, and I used to call people mad, because the spot it is set is precisely on a latitude. Precisely. I don't know if you see it. It's a bit out of focus. Can you read this? 2, 9, 9, 7, 9, 2, 4, 3, 5, 8 degrees north. Move the decimal places 4 points, you get the speed of light. Precisely. That's a very difficult pigeon to accept, because now it isn't just prime numbers and telling us this. I know, the speed of light, man. I know it's difficult. It is going against the grain of everything we know. It is frightening to consider this, but we're obliged to consider it. Like we're obliged to consider things that could be in different places at the same time because the physics exists. I use pigeons, so ducks, you know the order. This thing coos like a pigeon, flies like a pigeon. It walks like a pigeon, it eats like a pigeon, even looks like a pigeon. Must be a pigeon. How many pigeons are we going to need before we say it's a pigeon? Call me mad, but don't call Chandra Wickramasinghe mad. He thinks it's a blueprint. I'm going to stop here. Thank you.
Thank you, Robert. Great. Thank you very much.